Okay, we're gonna wrap up the last little part here of this chapter, and then off to the final one. So obviously we've been talking about complex ions, and we talked about how to sort of name our complex ions. Remember, it all this sort of revolve in terms of your, for example, counter ion and your complex ion. And you can have, again, a positive counter ion and a negative complex ion, or the opposite is true. You can have a positive complex ion and a negative counter ion. And again, when we go to sort of name it, it is sort of the complex ion part that's important for part of the name. We do name the ligands in alphabetical order regardless of prefixes. We do put the metal part of the name for the complex ion part at the end of the complex ion name with a Roman numeral. Remember, though, that if our complex ion is negative, we're going to roll with kind of those older school names that end in ATE, like ferrate, cuprate, zincate. If it is a positive complex ion, we're just going to use the regular old sort of metal name. In terms of the counter ion, remember as well that essentially we just kind of use the normal sort of names for our counter ions. So if it's a negative ion, we would call it IDE at the end, no matter how many we have. If it's a polyatomic ion, we would just use the name of the polyatomic ion. And then obviously in the front part, same idea. We would most likely use the name of the metal, which in most cases it probably would be. We also talked about oxidation number and coordination numbers. Again, um, remember that the coordination number is also based on the type of ligands that are attached to the metal and the complex ion. And some of them, again, are monodentate to combine sort of a one for one situation. There's some that are bidentate that gives you kind of like a two for one in terms of the coordination number. And there's some that are polydentate that obviously can bind in multiple places. So again, it is how many atoms are attached to the center metal in the complex ion that's important. We finished up talking about sort of isomers, and there are different types of isomers. There are some, for example, that are coordination isomers, where in one case the uh, molecule is a ligand, and in another case it may be a counter ion. We also saw linkage isomers, where the same ligand can actually attach via two different atoms within the molecule, and only one at a time, but can either use, for example, like the nitrogen or the oxygen to attach. There's also cis and trans isomers that occur. Again, cis means that they are same side, and trans means opposite sides. And in those type of isomers, we also can have chiral molecules that have non-superimposable mirror images, and this does happen sometimes with cis and trans, as the mirror image kind of throws a molecule to the back, and the connection ends up being different than it was in the original molecule. So instead of again having a maybe a connection between like these two guys, when it throws in there, it ends up coming to a connection like back there, and the mirror image again, although everything's the same, we'll end up getting something that will not basically superimpose. Any questions on any of those guys there? All right, the last thing we're going to talk about is actually sort of bonding in complex ions, and really sort of the distribution of electrons within a complex ion. Um, and the formation of hybrid orbitals to share electrons. Hopefully you remember hybrid orbitals, things like sp, sp2, sp3, sp3d, sp3d2. These typically are associated with certain geometries like linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral. Now Vesper doesn't work very well necessary with sort of complex ions. Again, we kind of look at it as we've been talking about more as a Lewis acid base situation. Um, but we can sort of use some of these ideas of hybrid orbitals as to how they sort of come together. And very common geometries that we see in complex ions are tetrahedral, which is typically like your four electron pairs, square planar, which is an expanded octet there that you find in the octahedral arrangement, where you have basically four bonds and two lone pairs, pairs of lone pairs. And we also have linear, and typically, thank you. These, as we will see, usually will basically coordinate to coordination number. These are typically a lot of the geometries that we see with a coordination number of four. Uh, Linear is typically a coordination number of two, almost like electron pairs, two electron pairs, two bonds is linear, four electron pairs, and so forth is tetrahedral. So in terms of the coordination number and the geometries that we typically will see, if we get to a coordination number of six, we typically see the octahedral arrangement. And again, like I said, kind of the square planar tetrahedral for our four coordination number. And again, our coordination number of two there. And again, this gives some different arrangements that occur. As for most cases, the metal within the complex ion is one of those transition metals. And when we talk about transition metals and sort of electrons and electron configuration, those are d electrons and d orbitals that we are talking about. And again, a reminder that there are five different d orbitals available. And in the absence of any ligand basically being present, these five d orbitals will actually all be exactly the same in terms of energy. So if you take a look at this, almost like an orbital diagram, in the absence of a ligand, all five of those d orbitals are going to actually be pretty equal to each other. What we're looking at here is coordination number of six and octahedral geometry here. And what happens though is as ligands get attached to these metals, there's actually a separation of the d orbitals, and they actually split off from each other. And this is typically what we see in the octahedral geometry. We get kind of those three non-squared ones on the bottom, x, y, y, z, and x, z, and up on top, kind of our squared orbitals there. And there is a difference in the energy of sort of those lower three orbitals and those higher three or higher two orbitals. And if you remember, when we fill electrons into orbitals like these, they do go in one at a time, right? To follow Hund's rule, and then they come back and would then sort of pair up in that case. And this splitting of these d orbitals affects sort of how the electrons will sort of populate these d orbitals within the metal. And this splitting is what is sometimes referred to as crystal field splitting, and that's basically the energy difference between the top orbitals and the bottom orbitals. So what can happen in certain situations, depending on the ligands that are present, is these electrons will go in and start sort of filling these d orbitals. And when they get to the end here, and obviously they would fill lowest energy to highest, they will look at this splitting here and go, well, that doesn't seem too bad. All right, I'll just kind of feel like normal and, come back down and kind of put my electrons in, sort of like we would normally expect it to happen. Now, in other situations, when that guy kind of gets to the end here, he may look up and go, that's pretty far away. That's a pretty big split in energy. I would rather pair up down here first before I'm forced to kind of go upwards. And depending on the ligands that are there and the sort of difference in the crystal field splitting, large splitting versus sort of small splitting, we will end up with these d electrons in different orbitals. The result of this is we will end up with electrons that are sometimes we end up with a lot more unpaired electrons, which is paramagnetic. And it is also sometimes referred to as a high spin complex because it has a lot of unpaired electrons. As opposed to that, we may actually end up with one where we have a lot of paired up electrons, and that is what is sometimes referred to as a low spin complex. So sometimes you hear about high spin, a lot of unpaired electrons, and low spin is more paired electrons. This, by the way, is paired electrons, right, where they have opposite spins within the same orbital, following Pauli's exclusion rule. Make sure they don't have the same four quantum numbers. This is obviously unpaired situation happening in that guy there. Now, the crystal field splitting, like I said, is that energy difference between the lower set of orbitals, d orbitals, and the higher set. And typically, what we would be looking at here is the transition metal in the middle of the complex ion. So that's the metal that we're looking at and the number of d electrons that it has. Now, how can we figure out the crystal field splitting? Well, as you may also know, they are very close in energy, our S's and our D's. And we do get the D's first, right, as we talked about earlier, and then the S's, for example, we can do something like that. And it doesn't take a lot of energy to sort of move around electrons from one place to the next. And we could actually calculate the crystal field splitting by using maybe an equation you might remember. And that's basically is E is equal to H times the frequency. That is basically our crystal field energy. That is Planck's constant. 6.63 times 10 to the minus 34 joules times second. And that is the frequency, right? And typically frequency is given in reciprocal seconds, RA hertz, basically, which basically the same thing. This guy and perhaps another equation you might remember, throwback Tuesday here, C is equal to the wavelength times the frequency. That's our speed of light, right? 3 times 10 to the 8 meters per second. That is our wavelength in meters, and that again is our frequency in reciprocal seconds. And if you put together both of these equations, as you might also remember, you get this version of it, E is equal to hc divided by the wavelength. And that means if you know the wavelength or if you know the frequency, you can figure out the energy associated with the splitting of these different orbitals. Couple of reminders, obviously wavelengths does need to be in meters when you use these equations for everything to cancel out correctly with, for example, the speed of light. And frequency should be reciprocal seconds. Any questions on that? This is something we're familiar with as well, right? When we do some type of like absorbance, right? We do want the maximal wavelength. So that's usually where we want to kind of set our, for example, spectrometer to get maximum absorbance. That's because, again, if we set it way over here, the wavelength, that's about all the absorbance we could get, as opposed to obviously all that in terms of absorbance. The other thing that we've talked about, hopefully, is the color, for example, of the solution that we see is complementary to the color of light that's being absorbed, right? And that's why when we have a red solution, we don't set the wavelength usually to the red wavelength. We set it maybe more towards a greenish, bluish type of area. And that's the complementary color to it. That is what you do on all those programs, right? Where it does the little graph and you move the little hand, and most of you eventually remember, oh yeah, I gotta lock that in to make sure it does record things, right? And we do those things. So I think this is filled out in your paper, so we'll just kind of go through the calculation just to talk about, how we get to the number. The absorption maximum of this complex ion is 470 nanometers. What is the color of the complex, and what is crystal field splitting? So once again, here at 470, that would put us in this area here. And obviously our complementary colors across the way. So the solution should appear orange to us as it's absorbing in the blue spectrum. Once again, in our red spectrum, we kind of set it over there in that 500-ish range, 490-ish range, and we get more of a reddish color. Again, we can, in this case, since we are given the wavelength in this case, which is 470 nanometers, nano is 10 to the minus 9 meters. And we can go into our E is equal to HC divided by the wavelength to figure it out. We do need to convert that to meters before it goes into there. Both of the top values are constants. And if we do that, we basically get a crystal field splitting of 4.23 times 10 to the minus 19. And that's really per atom. And if we wanted it per mole, we would incorporate Avogadro's number, convert atoms to moles. And again, we basically would multiply by Avogadro's number up on top, and that would give us moles. And our atoms would cancel in that case. And we end up with something like 255 kilojoules per mole is the crystal field splitting, which again is the energy difference between the lower set of d orbitals and the higher set of d orbitals. Within this case, cobalt here. This would have a coordination number of 6, which means you're probably looking at that octahedral splitting that we saw on the previous slide there. Again, 3 in the lower energy and 2 of those orbitals in the higher energy level. Now, how do I know if I'm going to end up, for example, with a high spin, low spin, big split, lower, smaller split? It does have to do with the ligands that are present. And there are some ligands which are considered weak filled ligands, and there are some that are considered strong filled. And basically, much like it might sound, if you have something on this end here, which is a strong filled ligand, if this was strong filled, that means that this splitting here, the crystal field splitting, which again, sometimes abbreviated actually was just a delta, is pretty large. And that means that when these electrons go in here, they're more apt to pair up on the lower energy before they would go to the higher. Now, if you had something, say, on this side, that is the ligands that are attached in your complex ion, that splitting between our higher d orbitals and our lower sort of d orbitals here is going to be relatively small as it's weak filled. And that's going to mean that we would expect our electrons to kind of just feel like we normally would, kind of go through each one individually and then come back and pair up. This, as you can see, is going to give us a lot more unpaired electrons here. And this is typically what leads to what is sometimes referred to as high spin versus obviously low spin over here where we have more paired electrons sort of happening in this case. Now, what happens with the ones in the middle? Well, they kind of go both ways. You can maybe end up with a low spin or high spin. Sometimes they will tell you do it for maybe a low spin complex or a high spin, or they may say do it for strong field or weak field. And they'll sometimes give you some indication as to maybe, which way you should do it. Sometimes if you're not given any indication as to how you should draw the electrons in this sort of picture, sometimes it actually doesn't matter. So for example, if I only have 3D electrons to distribute, I'm never getting out the bottom part here. I'm not going anywhere past there, so it really won't make a difference. So sometimes if you're not given any type of indication and you're like, I'm not sure which one to do, sometimes it just won't really make a difference, because you're not going to really get too far into the electrons there. So if we take a look, say we'll take a look at, we'll do this one here. So if we take a look at this guy here, and first off, the coordination number here is going to be 6, which means we are going to get the octahedral splitting of those d orbitals, which again is what we've been looking at, 3 on the bottom, 2 on the top, all the squares up there on top. So in this case, if we take a look at this, bromine is -1. There's 6 of them, -6. Overall, -2. That means here our oxidation state on our nickel is a +4 situation, I hope. We go to nickel on the periodic table there, looks like a 28. That means if we wrote the electron configuration for nickel with no charge, we're looking at something like argon 4s2 3d8 in this case, as it is 28 there. Now, obviously here, nickel with a +4 charge means that it has lost 4 electrons. And as we talked about earlier, as a reminder, when transition metals lose electrons, they are going to lose the S's first, which means we're going to lose 2 electrons there. We will then pick the other 2 out of there, and we will be ending up with argon 3d6 in this case. And again, as I mentioned earlier, this is sort of the importance of understanding electron configuration for these guys, because basically here we now have 6 electrons to distribute in that sort of crystal field splitting. So since it is going to do its splitting here, again with our sort of squared guys up on top, what we then want to look at is we want to look at here our bromine. And our bromine, which is over here, this is a weak field splitter. And weak field would mean that we have a small splitting happening here. And that is weak field. And that means that when we go to distribute our electrons here, we're going to go 1, 2, 3, because this is going to be sort of a small difference occurring here, 4 and 5. And we will come back and pair off on the bottom here. And a very common question that you're asked about these things is basically how many unpaired electrons will you end up with? And you end up with 4 unpaired electrons in this case. And obviously, as you can see here, any questions on that there? All right, so why don't you try this one here and draw the crystal field splitting, figure out how many unpaired electrons you should have. Okay, so let's take a look. So we're doing this one, I think. All right, so if we take a look at this one here, once again, we kind of want to figure out a few things. Coordination number here is going to be 6. That's monodentate, which again tells us we're going to get the octahedral usually splitting here. So we are going to get our kind of 3 on the bottom there, 2 on the top, our squares up there. Again, looking at our oxidation state for our iron, that's -1. There's 6 of them, -3 on the back end there, so +3, I think, in this case. Iron, again, with no charge is looking like 26, so that is going to get you an argon 4s2 3d. What do we have there? 8, I think. What am I thinking? 1, 2, 3, 4, 5, 6. 8, too far. 3d6 there. That then means our iron in this case is +3. Once again, going to take out those. We're going to take 1 out of there. So that's going to leave us a argon 3d5. I can write my 5 there. And it's those 5 electrons that we, again, want to distribute here within our crystal field splitting. And we can look at our ligand in this case, which is Cn-. We come back to our spectral series here. We do see Cn- on the strong field splitting side. That means that we are going to get a strong field here. This is going to mean that we're going to have kind of a big split that's going to occur in this case. So as we go to distribute these 5, 1, 2, 3, is going to go, no, thank you. I don't want to go on top. 4 and 5 in that case. And here we will end up with one unpaired electron. This would be again considered a low spin complex as we only have obviously one unpaired electron, as opposed to our previous one here where we did have four unpaired electrons. This again would be considered a high spin complex because of the number of unpaired electrons there. So again, lower number of unpaired electrons considered low spin, more unpaired electrons considered high spin. Any questions on that there? Yeah. It's always going to start at the bottom. So electrons will always right fill lowest energy to highest. So in this case, no matter what the sort of ligand is, strong field or weak field, it should start to fill at the bottom because it's lowest in energy. The key is because of like Hund's rule and sort of Pauli's exclusion rule, but mainly Hund's rule, maximum stability happens where we have parallel spins. We're all heading the same direction, the arrows or the electrons. The problem is when they get to the end of the bottom, which is the lowest energy, they then have to decide, do they want to jump way up there if it's a big split, or if it's not such a big energy difference, they will go up and continue to maximize the parallel spin, because this energy difference between the high and the low is not really large enough to cause them not to do that. If you get a strong field, what happens when they get to the end, they go, I don't really care too much at this point about that kind of maximizing parallel spin. I care more about that's way too much energy for me to go up there at this point. I'm going to kind of pair up on the bottom first before I go to the top. So is that decision of, as they're filling those lower ones, they get to the end and go, well, is that kind of too big to go up there? And if it is, in terms of energy, they would rather just do the bottom first and not have to deal with trying to get up there unless they're forced to. They have enough electrons and they fill up the bottom, then they got to go up there because there's nowhere else for it to go at that point. Yeah. Other questions? All right. And again, here's a couple of examples of obviously here on the left, you can see high spin with the fluorine, creating a, whoops, come back, a more weak field. Again, in this situation, as they get down here to distribute the 5 electrons, it's not going to have a problem and it's going to be able to kind of fill it and again maximize that parallel spin. Over here, again, with the one we just did, they're going to go, no, thank you. I'd rather just go to the bottom. It's just too much energy to kind of get up there if I don't have to do that in this case. Here's all your different combinations on the left. All of them are more weak field on the left. The splitting between the lower and the higher are much smaller, leading to a lot more unpaired electrons. And again, a more high spin complex is occurring as opposed to the right-hand side, where the splitting is more strong field, creating a lot more paired electrons and unpaired electrons in that case. And again, what we're specifically been looking at here is for octahedral arrangement and coordination number 6. This is a tetrahedral arrangement, and this is now a coordination number of 4 and not 6. It's basically identical to octahedral splitting, except it's upside down in a sense. The kind of ones that were lower in energy originally are now higher in energy, and the ones that are obviously were higher and is now lower. Works the same way. You would obviously fill down here and then decide, do you want to go up to kind of fill or not, depending if it's strong or weak. If it is strong, they would probably fill the bottom 2, then go up. If it is weak, they would go fill the 2 on the bottom, not completely, and then go up and individually fill it. And then obviously here, this is square planar, which is also a coordination number of 4. A little bit more craziness here in terms of our splitting that's happening in this case, but again, works basically the same idea as we go through it. Now, for us, you will not be responsible for square planar because it looks crazy. But you are responsible to know tetrahedral splitting, which is basically just the opposite of the one that we've been talking about, which is octahedral splitting. So you're responsible for those two in terms of splitting. Any questions on that there? And again, like I said, very common questions on these type of ones are, draw it, and how many unpaired electrons is a very common sort of thing. And do you have like a high spin, low spin sort of situation? All right, any questions on that there? That wraps up this chapter, I believe. All right, that brings us to the very last chapter, which clearly is not 18. It was close. I think it's 21 here. All right, so last chapter of the season here, which is nuclear chemistry, chapter 21 here. We'll talk about glowing in the dark, maybe. We'll see. Talk a little about radioactivity. And when we talk about radioactivity, this is typically the idea of unstable nucleuses will really start to decompose sort of spontaneously and go through what's known as radioactive decay. Um, they typically will, if you start with, or whatever you start with as the unstable guy, that is usually referred to as the parent nuclei. And whatever it sort of decays into is sort of referred to as the daughter nuclei that comes from it. Nuclide is basically the new nucleus is sort of formed, or the nucleus is formed in those isotopes. Anything on the periodic table there, about 84 or more, or you're looking at things that are radioactive, that usually brings you to like the bottom row there on the periodic table. That's also, as we'll talk a little bit about, is where we get all the like man-made elements, right? With all the nice names like Einsteinium, Nobelium, all those kind of things happen there as well. Now, as we will talk about, there's a couple ways that things kind of go through a decay process. Sometimes it's just natural. Sometimes you can force it to sort of start through a process where it starts to split off into new things. There are different types of radioactive decay, and you remember our good friend Rutherford. He did something with gold and foil in an experiment, and he shot things like alpha particles at it, right? And alpha particles have the symbol with the alpha symbol and a 4 and a 2, or because it's nuclear chemistry, there's 400 different symbols, but it's basically a helium nucleus. And you can use the alpha symbol or the helium nucleus is commonly used both for alpha particles because that's basically what it is. By the way, number up on top is the Yes, it is the mass number. Good answer on that there. The number on the bottom is the atomic number. Yeah. And the atomic number is the number of protons. Yes. Mass number is the number of protons plus the number of neutrons. You can find the atomic number on the periodic table. Do we find the mass number on the periodic table? The answer is no, we do not. So the number on the bottom is not the mass number. That is the atomic mass. The mass number, atomic number, protons, electrons, neutrons, all should be positive whole numbers. So again, those only the atomic number can be found up there on the periodic table. Obviously, out of all of our subatomic particles, our protons, electrons, and neutrons, the one that is the most important in terms of what element you're dealing with is which one? Is the protons there, yes? That's because if you look at the periodic table, everybody has a different atomic number, which means everybody has a different number of protons, and the number of protons is what determines what element you are dealing with, which is really important in nuclear chemistry. Beta particles or beta rays is the beta symbol with a 0 minus 1, or if you like an electron, because it's sometimes basically just an electron. People will sometimes use the E for that. We also have gamma rays. Gamma rays is pure energy, very short wavelength, high in energy. If you remember the electromagnetic spectrum, gamma rays is all the way there at the end of it with a very short wavelength and very high energy. In addition, some other particles that we sometimes come across here in nuclear chemistry, positrons, they are like electrons, but with a better attitude. Thank you for laughing. I appreciate the help there. They also used really the same symbols as you see for beta particles. So you can use the beta symbol and the electron, but one's plus one, one is minus one. If by some chance you see just a beta symbol, nothing else written there, it's probably pretty safe to assume that's going to be the beta particle. Usually, if they're talking about the positron, they'll incorporate the positive sign somewhere. So even they may just put like a positive up here, which would tell you it's more of a positron rather than a beta particle. Again, I would say if you just see the beta particle, probably pretty safe to assume that or the beta symbol is just a beta particle. In addition, we could have an electron capture, which is basically the same sort of symbol as for an electron here. So as we talked about, it is the number of protons, which is most important, which is typically that top number that we write on isotopes. Here's just a chart of some of the stuff that we went through. A couple of other particles that we see a lot is a proton, which is sometimes abbreviated with a P and a 1 and a 1. Our proton is really just hydrogen, which is a 1 and a 1. A neutron is definitely a symbol that we see a lot in our nuclear chemistry. Now, one of the differences, right, between, as you may know or not know, differences between a nuclear reaction and a basic chemical reaction is in a chemical reaction, we do get the conservation of all the elements. And that is because in a chemical reaction, which we mostly deal with in general chemistry, only involves breaking bonds and making bonds when you do a chemical reaction. That's all electrons. Has nothing to do with anything in the nucleus. And that's why when we balance a chemical equation, we need to make sure we have the same number of elements on each side because we never change elements. In a nuclear reaction, it is all about changing what's in the nucleus. We change protons to neutrons, neutrons to protons. So we do not get really the conservation of elements like we see in a normal chemical reaction. You will start with one element and make something different as the result of a nuclear reaction because it is all based on what's happening in the nucleus. Now, depending on the type of emission, and when we talk about emission, that is usually some type of particle being given off, and alpha particles, beta particles, and gamma rays, they do penetrate further in, for example, pieces of lead and also your body as well. So if you are ever working with anything that's radioactive, you should make sure that you understand what type of emitter it is, as is very important to make sure you have the right protection. You know, sometimes people just throw you in and go work on this. And you're like, oh, no, I'm glowing now. That's not so good. Some things you may just need gloves and stuff, and some things you may need some leads, some concrete, and you need some distance from when you're working it. Actually, alpha particles don't penetrate us for far as beta particles, and obviously gamma particles, which is very high in energy, penetrate very, very, very far. Here's a table in case you didn't like the first three that we saw, but the same symbols. And as I mentioned before, this again, some also very commonly for those, you can see one has a minus, one has a plus. Now, when we talk about balancing nuclear equation, it is really super, super hard. So you want to make sure you pay attention here. I'm just kidding. It's really just adding. That's pretty much all you have to do. Because in a nuclear reaction, as I just mentioned, we do not have conservation of elements, so we do make new elements along the way. We do balance nuclear reactions a little bit differently. And basically, to have a balanced nuclear equation, there's basically two things that you have to make sure of. Basically, when you add up all the mass numbers, which are on top there on the left-hand side, they need to equal the exact same mass numbers on the right-hand side. So if we do a little addition here, that's a 236 total. We got 138 and 96 and 2 also equals 236 on the right-hand side. By the way, as you can see here with the coefficient, you do have to multiply both of those numbers by the coefficient because you basically have two neutrons, right, in this particular case. So you want to make sure you do that. And then the other way that we balance it is by atomic number. So same idea. When you add up all the atomic numbers on the left-hand side, they need to equal all the atomic numbers on the right-hand side. And then you will have a balanced equation. So for example, what you oftentimes may have is an equation where maybe something is missing, right? So you got something like this. So you may have something missing, and basically the best place to start is atomic number. So again, we got 92 on this side. If I were to do this, that's we got there 37. If I subtract those two, that's going to give me really my missing atomic number, which is 55. And because you could find the atomic number on the periodic table, you can then go to the periodic table and find number 55, which will tell you we are talking about cesium. To do the top, we would do the same. Again, we would have 236 on the left. What I got going on here is like 98. If I subtract those two, that's going to give me, again, our missing atomic number there, 138 there in this case. So I would have definitely attacked the atomic number first, use the periodic table as kind of your friend when you're doing these, and then get the missing mass number. Now, it is possible that if something is missing, it could be a particle. So it could be some type of particle that is missing, either an alpha particle or beta particle. Now, when we have an equation like this where something is missing, that is one way you can approach it. Sometimes you are, though, given things in words. And if you're given stuff in words, there are a couple of words that kind of help you understand maybe where you should put things. So if it says something like this thing goes through an alpha decay or an alpha emission, anything that's going through some type of decay or alpha emission, those things end up on the product side. If it's something being emitted, going through some type of decay. So I would put my alpha particle on the product side if we were talking about that. If we're talking about beta, it would be a beta particle. You could have something that is like an electron capture, or you bombarded something. Those guys go on the reactant side. So if I were doing an electron capture, I would put my electron on the reactant side. So sometimes you're given things in words, and those are some common sort of words that are used on up there. All right, so let's take a look at one here together. So we have PO212 decays through alpha emission. So through alpha emission tells me that I should put my alpha particle on the right-hand side, which, by the way, you could use the alpha symbol, or if you wanted to, you could use the helium symbol as well. Either one is perfectly fine. I would probably go to my periodic table and find PO, which is up there somewhere. What number is it? It is right there, 84. 84. And that would give me really my missing atomic number in this case. That was not provided to me. Now I'm basically looking for sort of what's going to form on the other side. So all we have to do is start with our atomic number. We got 84 on the left, 2 on the right. 84 minus 2 is 82 for our atomic number. And if we go to the periodic table, we can see number 82 is lead. Now doing the top there, we got 212 on the left, 4 on the right. So that is a 208. And now we have a balanced nuclear equation. If we add up all the mass numbers, on the left is 212. On the right, we got 4 and 208 is 212. On the left, we got 84 and 82, and 2 on the right is 84 in this case. Any questions? Not too bad, just, a little bit of adding in a periodic table. It's pretty good. As I touched upon a second ago, the major difference between what we normally study, which is chemical reactions and nuclear processes, is, again, it's all about electrons, bonds breaking and making. We never change the element. We never do anything that involves really the nucleus in those type of reactions. As I mentioned earlier, in nuclear reactions, it's all about that. And again, we convert protons to neutrons, neutrons to protons. And in that kind of conversion of everything that happens in the nucleus, that is what really releases, for example, like a beta particle or an alpha particle. It's kind of the leftover that happens as you kind of make the new protons and neutrons as they kind of do that. And just to illustrate that here, we'll take a look at some of these decay processes and sort of maybe what's going on here. We're not going to worry about the neutrino here. It has really no mass or anything like that. But here is a beta decay. And in a beta decay, what's essentially happening is we're converting a neutron into a proton. And as a result of that, a beta particle will be emitted there and sort of released. Now, overall, what happens is the mass number really doesn't change overall. And the atomic number actually needs to go up by one because we end up with a -1 on the bottom. But it does really change if you kind of do it like step by step, which is definitely not correct what I'm going to show here, but you get the idea here. We're going to lose a neutron in this case. And since the top number is protons plus neutrons, and this is protons, we're going to lose really a neutron in this case, which would take us to 13, 6, and carbon. But then we're going to form a proton, which would be added here and here, which would then take us to 14 and 7. Now that I'm at 7, I'm no longer at carbon. I have now moved over there to nitrogen in this case, along with this beta particle that's going to come off in this process as well. So although it appears that maybe the mass number really doesn't change, it actually does change because we are converting a neutron in this case to a proton. Overall, number-wise, it doesn't change, but the protons and neutrons sort of individually have sort of changed. Same idea here with a positron emission. We're basically going to convert a proton into a neutron in this case. So again, if we take a look here, it may appear that maybe nothing happens to the mass number. But as we lose that proton, we're actually going to take one out of each of these, and that's going to take me to 10 and 5. That also will change the element from obviously where we started there, which was 6, to our boron, which is 5. Then we're going to form a neutron, which would put one back into there. And again, that's how we end up with the same number, but there is some transitioning that is happening between protons and neutrons in this case. Electron capture, as you can see here, an electron capture is on the reactant side. So again, in words, capture, which is the electron capture is the most common one, or something that's bombarded is going to put that particle on the left-hand side there. Alpha decay, what's happening here is a proton and electron are actually coming together to form a neutron. And once again here, it doesn't appear too much happening on the mass number, but we are losing a proton, but then putting back a neutron. So basically our mass number on top goes from 37 down to 36 as we lose the proton, but when we put the neutron back in, it goes back up to 37. So again, doesn't appear too much changing. Probably the biggest change that you're going to have is a alpha decay, which changes again the mass number by 4 and the bottom number there by 2. It results in really a decrease in 2 neutrons and a decrease in 2 protons. Is kind of your biggest change that occurs. Now, fission is the process in nuclear chemistry where basically we start with something that's unstable. It will split off into 2 new nucleuses. It usually will release a bunch of neutrons and a bunch of energy along the way as well. And in a fission reaction, it can be spontaneous, which means something is unstable. It will just start the decay process by itself. You could also, again, like I said, kind of shoot something at it and start that process where it will split off. As we'll talk a little bit about, what you actually make on the other side is not 100% predictable. You don't always get the same 2 things when it splits off along the way, so you can get different things. So just a chart of some of the things we've been talking about there. So why don't we take a look here again at potassium 40. So 40, once again, when it is written like this, is the mass number. Yeah. We can again go to the periodic table there and pick up our atomic number, which is 19. And in this case, it is doing a positron emission. So emission means that our particle should be on the product side. It is a positron emission, which means we could use the beta symbol or the electron symbol, but it is +1 on the bottom there. And now we could kind of find kind of what we're missing. So looking at the atomic number on the bottom, I got 19 on the left and 1 on the right. To get them to equal each other, my missing atomic number is 18. I again could go to the periodic table and look at number 18, and I will see our friend argon there. And looking at the top, we got 40 and 0, which means our missing mass number is 40 in this case. And again, now we do have a balanced nuclear equation. Questions on doing that there. All right, I tried some. Why don't you try some? Yeah. All right, so for each of these, write the balanced nuclear equation. Once again, when it is written like this, uranium-238, again, this is the mass number. We again can find the atomic number from the periodic table. So we're going to start with our uranium-238. Going to the periodic table, we see uranium is number 92 in terms of its atomic number. Alpha emission means that we are going to get a alpha particle on the product side. And again, it's up to you how you want to write it. You can use the helium, you can use the alpha symbol, whichever way that you like. At this point, we pretty much have everything that we need. We just need to figure out what we're going to form here. So going on the bottom here, that's 92 on the left, 2 on the right. We subtract those two numbers, we are left with 90, which is sort of our missing atomic number. We go to periodic table, number 90 is TH. Doing the mass number next, we got 238 on the left, we got 4 on the right. Once again, if we subtract those, that leaves us a 234 in this case. Any questions on that one there? Beta emission of neon 24. So once again, starting with neon and 24 up on top, go in the periodic table. Neon is number 10. Emission again tells us this is on the product side. And beta particle, again, can use the beta symbol, could also use the little E for the electron if you like. And now we can figure out what's missing, starting with the atomic number 10 on the left, -1 on the right. We actually do need to go up 1 to 11. That way 11 and -1 there gives us 10 on the right. Number 11 on the periodic table is sodium. And doing the top there, 24 on the left, 0 on the right. We would need 24 in this case. Positron emission of nitrogen 13. So again, nitrogen 13. We could get our periodic table will give us nitrogen's atomic number, which should be 7. And emission again means product side. So in this case, it's going to be a positron on the product side. And again, it is +1. You can use the beta symbol or the E. Missing sort of atomic number, 7 on the left, 1 on the right, leaves us 6 left over there, and that's going to be carbon. And 13 minus 0 is 13 in this case. Lastly, we have an electron capture from beryllium-7. So beryllium-7, atomic number from the periodic table is 4. And in this case, though, electron capture means that the electron is actually a reactant in this case. So it's not going to be on the product side. So again, common words, capture, bombarding something, that's going to be that particle on the left-hand side of the arrow. Here we're just going to add basically. So 4 and -1 is 3 is our missing atomic number. And go in the periodic table, 3 is lithium. And up on top there, 7 and 0 is 7. Okay, so any questions on writing or balancing nuclear equations? Or not too bad. Okay. All right, then let's continue on. We're now going to talk a little bit about stability, and there are different ways that we sort of measure stability. And one of the ways that we can measure stability is what is sometimes referred to as the N to Z ratio, N being neutron, Z being atomic number. So basically neutron to proton ratio here is basically what we're looking at, neutron to proton. And there is a sort of ratio that is stable for everybody. And that is what is sometimes referred to as the valley of stability, this ratio, or the belt of stability, depending on your textbook. And if this ratio is too high, so you find yourself sort of on the high side here in terms of that ratio, what happens is neutrons get converted into protons, and it will go through a beta decay to kind of bring that ratio down towards a more stable ratio. Will it perfectly be able to get it stable after one sort of decay process? Not necessarily, probably not, but it should move the ratio closer to that valley of stability or the belt of stability. If your ratio is too low, like you end up on this side, we need to convert some protons to neutrons, and that will bring our ratio back up towards the value of stability. And it could actually do this two ways. You could either do a positron emission or an electron capture. You could also do an alpha decay, but it's not as efficient, so we're not going to use that for us. So it will either do a positron emission or an electron capture. And you may be saying, would I get something different if I did either of those? So we could actually use this one we just did as an example. This is an electron capture. If I'd started with the exact same thing and did a positron emission, it would look something like this. And my missing atomic number would be 4 minus 1, which is 3, and 7 minus 0, which is 7. And as you can see, you will end up with the exact same outcome here. So that's why on that particular one, you do have an option of two. They both should give you the exact same outcome, either a positron emission or a electron capture. Now, how do I know if my ratio is too high or too low? We do look at the valley of stability or the belt of stability, which is sort of that yellowish smear there. And the acceptable ratios does depend on the atomic number of what you're looking at. So if you have an atomic number between 1 and 20, an acceptable ratio is basically a ratio of 1. If you're between 20 and 40, 1.25. 40 and 80 in terms of the atomic number, 1.5. Anything above 83, which would take you 84 and above, will be radioactive and not stable at all. Now, we're going to use these cutoffs as sort of hard cutoffs. And that is because there is some gray area. As you can see here, this one goes to 20, this one starts with 20. So sometimes the books will go, well, it's kind of in that range of 1 to 1.25 is in that grayish area if you have 20. And this one obviously ends at 40, and this one starts at 40. So for us, we will use these as hard cutoffs. Either it is that number or it's too high or too low. I obviously will not try to intentionally give you anyone that's in that grayish area, but you may come across some in the book that's sort of in a grayish area, and those kind of go, it's okay because it's in that sort of area. So let's take a look and see how we can figure this out. If we take a magnesium 22, the first thing we want to look for is what is its N to Z ratio here. So I need to figure out the number of protons, and I could get the number of protons from the periodic table. Magnesium is number 12 there, which means it has 12 protons. The number of neutrons is the mass number minus the atomic number. So in this case, the mass number is 22 minus our atomic number, which is 12. That gives us 10 neutrons in this case. So if we calculate our N to Z ratio, we're going to take 10 divided by 12, and that's going to get us here 0.8333. Now, when we look at the atomic number here, which is 12, that puts us at our first sort of cutoff here, our sort of 1 through 20. And our acceptable ratio here should be 1 in this case. So an acceptable stable ratio should be 1. When we look at this, this is too low in this case. So the first thing it's going to tell us is we're kind of down in this area. we need to bring it this way, and it's unstable. So remember that as we saw on this slide, if our ratio is too low, you're going to get one of two options that could occur. It could either do an electron capture, or it can again do that positron emission, which, as we just saw, basically gives you the same outcome. So if we take a look at this, what's going to happen in this situation is the magnesium 22 will go through either an electron capture or a positron emission. And we will end up with 11 as our missing atomic number, which is sodium, and up on top 22. Or it will go through an electron capture, which would look something like this, 22 and 11, and sodium. Again, you're going to end up with the exact same thing. Now, did we sort of help ourselves out here? If we take a look now at what we just formed, which is sodium 11, or sodium 22, number of protons is 11. Number of neutrons in this case is 22 minus 11, which is 11. And dare I say, my N to Z ratio now looks a lot better. It is in a ratio of 1, which actually puts us perfectly stable in this particular case. This will not always be the case. It will not always, after the first decay process, hit perfectly stable. But once again, it should be moving you towards that valley of stability in terms of its ratio. You do not typically on these type of problems need to keep going until you get something that's perfectly stable. Just kind of do the first decay process that it will undergo. Any questions on that there? All right, so once you try one here, how about Krypton 85? Krypton is 36 on the periodic table. Is it stable? If not, then write a nuclear equation for what it should go undergo. All right, so again, Krypton 85, 85 being the mass number, we could get our atomic number there from the periodic table. That's going to tell us, obviously, here we got 36 protons. Our neutrons there are going to take the mass number, which is 85, which is protons and neutrons, minus the atomic number, and that's going to get us 49, I believe. And in this case, we could do our N to Z ratio here. So it's going to be 49 divided by 36. That's going to get us a 1.36. This being an atomic number of 36 would fall in the 20 to 40 range, which means the acceptable ratio is 1.25 in this case. 1.36 looks higher there, so we are too high in this case. We want to kind of bring us down to that valley of stability. So when we're too high like this, we're looking at a beta decay that's going to occur. So if we wrote our equation here, we would have this beta decay coming off. Going to have to go to 37 in this case because of the -1. Again, going to periodic table, 37 is RB. Up on top, 85 and 0 is 85 in this case. And again, if we take a look at what we just formed, our neutrons would be in this case now 85 minus 37. So 85 minus 37, 48. Our protons are 37. So 48 divided by 37 for our new sort of ratio after the decay process is going to be 1.3. So it did come down. It didn't get a perfect ratio. And again, as long as it's moving sort of in the right direction is what we're looking for here. Questions on this? So this is one way, again, that you could look at stability, the neutron to proton ratio. Question? Yeah.
So you won't always get that value that you're looking for, but
Correct. It should be moving in the right direction. Yeah. So before we did it, it was 1.36, right, which is high. And now we brought it down a little bit to 1.38. We're moving closer to that belt or valley of stability, right? If it was 1.36 and then you got higher than that, you're moving the wrong direction, obviously. Yeah, ideally things that are sort of radioactive will continue to decay until it, ideally hits something that's a little bit more stable. Um, you don't need to do that in these type of questions and stuff like that. Yeah. There's something we'll talk about which is known as a decay series, and in a decay series, that's basically what happens. It just kind of keeps going one after another until it hits something that's really stable. Yeah. Now, that's again one way to look at stability. There's a few other ways or a couple other things that sometimes people look at. In addition to the N to Z ratio, a lot of times we find the most stable sort of nuclei when we have even numbers of protons and neutrons. So if you take a look at sort of this table here, we have 157 nucleuses that are stable when you have even and even in terms of protons and neutrons. The next best situation is like even protons, odd neutrons. You got 53 odd protons, even neutrons, about 50. Worst situation and stability is if you have end up with like odd of both of those things, protons and neutrons. There's only five sort of stable nucleuses that are that way. So if you got like a positive on protons and neutrons, that's usually a fairly good symbol or indication that you might have something that's going to be pretty stable. And at least something that's positive out of those two will get you something that's maybe going to be stable. But worst case scenario is it's all odd. Also, when we add up nucleons, and that's a word that you sometimes hear a lot in nuclear chemistry, and nucleons is basically the particles within the nucleus, it's basically your neutrons and your protons, and those are the particles you find in the nucleus. They do add up to magic numbers, makes them more stable, kind of like an electron configuration when things try to get to the noble gas configuration, sort of same idea. Things are a lot stable when neutrons or protons are add up to or 2, 8, 20, 28, 50, 82, and your Powerball number there is 126 there for your neutrons. And then again, those are just some good sort of numbers in terms of stability. A lot of those sort of positive numbers there as well. Any questions on that there? All right, we're laid up there for today.